In this lecture, we are going to discuss the magnetic field created by a toroidal magnet or coil, basically. So what is this toroidal coil? So if I start with the solenoid, which is just this cylinder, which has coils of wire wrapped around it like that, then if I want to make a torus out of it, then I would bend this tube and connect the ends. So I would end up with something like this, where we've now have a kind of a donut-shaped tube, and we've wrapped coils of wire around it. So you can take one wire and then just start wrapping it such that, you know, you could have a current entering here, and then on this wire the current is exiting in here. And from our discussion of the solenoid, the magnetic field of the solenoid, we said, was along the axis here. And so in the torus, we would expect then that the magnetic field would kind of circulate inside the tube of the torus. But that's what we want to prove mathematically, and not just draw a pretty picture. So, okay, so the first thing that we've done in all the cases where we tried to find the magnetic field is first find the direction of it, and then find the equation that'll give us the strength of the magnetic field later on. So to find the direction of the magnetic field, which I said I hinted was probably circulating inside the tube, we can start with the Biot-Savart law. Which basically says that this infinitesimal, or this differential of magnetic field is equal to mu 0 divided by 4 pi. The current, which the book gives a direction to, crossed into the radial direction, divided by script r squared, and then dl. Okay, so what do all those symbols mean? That's the equation. So how would we draw it? So we have the choice of how we want to orient the torus. And so if I start with my Cartesian coordinate system, then what I'm going to do is I'm going to draw the torus in the xy plane right here. And so that means what I'm going to do is I'm going to pick a point which is going to be the distance r from, say, the axis. I'm going to find the point where the current is, and that's going to be my distance r prime. No, I'm sorry. I'm going to first find the distance from the origin to the current. That's going to be r prime. And then that means this distance here between r and r prime is script r. So let me go back and label these vectors. Okay, so those are the distances. So we have a current element right here, which is in the coil of wire. We have a dl that we're going to eventually integrate over. But so these are all the all the different positions that we have. So we're going to measure the magnetic field at some point up here, a distance r away from the axis. Okay, so then let's write out these different vectors. So r prime is going to be equal to s prime cosine theta prime in the x direction plus s prime sine phi prime in the y direction, and then just z prime in the z direction. Okay, so what is S prime? Well, S prime is the radius of my of my torus. So it would be this distance. Like, so we could pick one. It would be this distance right here. So this is the coordinates for the vector for the source where the current is. The vector for where I'm measuring it, r, is going to be x prime plus z prime. So we've just decided to measure at that one point, not on the y-axis, and so that means that my difference vector is going to be r minus r prime, or basically x minus s prime cosine phi prime in the x direction, plus minus s prime sine phi prime in the y direction, plus z minus z prime in the z direction. And so now if I write down the direction of the current is the current in the radial direction, in the s direction, plus the current in the z direction. Or you can actually, we will probably want to write this out in Cartesian coordinates. And so that current would be is cosine phi, so that's the x direction, plus is sine phi in the y direction, plus iz in the z direction. Okay, so now we have to work out, now that we have the current and we have the r vector, then we can create the cross product between those two, which would be this right here. It'll take me a second to write it all out. Okay, so that's the cross product. And now when we perform the cross product, what do we get? Well, we get, in the x direction, we would have s sine phi prime times z minus z prime minus a minus, so plus iz s prime sine phi prime, so that's the x component, minus the y component, which would be is cosine phi prime times sine minus sine prime, minus iz x minus s prime cosine phi prime, like that. I'm running out of space. And in the z direction, we would get is cosine phi prime minus sine phi, and then there's also an s prime in there, minus is x minus s prime sine phi prime cosine phi prime. Okay, so now we have all of those components. Okay, so what are we going to do with that? How are we going to clean this up? Well, what we could do is factor out some stuff. So I would have x sine phi prime is z minus z prime plus iz s prime minus y, and I'm actually going to leave the cosines there for a second. And we get yeah, I z x. I'll make this plus. I z x minus s prime cosine phi prime minus is z minus z prime times cosine phi prime plus z, and then essentially minus is x sine phi. Because that is times s prime times sine cosine cancels. Okay, so what do we have? So this is our result. And what's the interpretation of this result? Well, the interpretation then is that we have basically a symmetry where if I looked at the torus and I looked at a slice of it like so, I could basically look at symmetric pieces where this piece over here is at an angle of minus phi prime, and this piece over here, which I haven't drawn out correct all the way, would be at an angle of phi prime. And so, well, let me draw that again. Basically what you have is that on either side of the x-axis it looks symmetric. So the magnetic field created by the angle that is phi prime would be canceled by the angle that would be that of minus phi prime. And so there would be a canceling of that with the x and z components. And the only thing we're left then now is with the y component. And so what you would have is this y I z x minus s prime cosine phi prime minus I s cosine phi prime, which I can then generalize back to being in the phi direction. So in the end, what we find through this exercise with the Biot-Savart law is that indeed, with the toroidal magnetic field, that it should be inside the torus coil, and it should then just circulate inside the tube. Okay, so in the next lecture, what I'll do is something very simple, and that is just to work out what is the now functional form for the toroidal magnetic field.